Previously, we mentioned that there are at least 9 different conditions of the column that will give you unique design in terms of the calculation step to determine the amount of reinforcement bar in the column. So far, we have gone through a series of questions for the column under different conditions. The column can be short or slender. It can be unbraced or braced, and the moment can be acting in the major axis or the minor axis. So far, we only managed to cover the uniaxial bending moment. That means among this series of columns, we have yet to cover the moment acting in both axes. Short column subjected to both axis moment. Slender braced column subjected to moment in the both axes, as well as slender and unbraced column subjected to moment in the both axes. Therefore, for these questions and the following questions, we're going to deal with this type of columns separately. First, let us deal with the short column where the moment is acting in both axes. We use the similar specifications and the details of the column, except that we modify a bit in terms of the loading acting onto the column. You can consider this as a totally new column, and we shall go through the calculation step in order to demonstrate the calculation process to design this column. These are the specifications. Concrete grade 30, steel bar grade 500, exposure class XC3. The effective length and the slenderness ratio we adopt from the previous example, dealing with the braced structures, short columns previously, that we did the calculations to determine the slenderness of the column. Next is about the loading. NED equals to 147.36 kN, and the moments are given here. This is the moment acting on the upper end of the column and the moment acting on the lower end of the column. As for the reinforcement, tentatively the main rebar is 16 mm and the shielding is 6 mm. The dimensions of the columns are given here. 150 times 300. A larger moment acting on the major axis, whereas a smaller moment acting on the minor axis. Without further ado, let us look into the solutions. The calculations start with determining the nominal cover. This you may refer to the Eurocode. Your nominal cover is determined by the C-mean plus the deviations. The recommended value for the deviations is 10 mm. As for the C-mean, it is governed by 3 parameters here. First is due to the bond requirement, second is due to the environmental conditions, and third will establish the minimum C-mean. C-mean bar here, you can get it from table 4.2. It is defined by the diameter of the longitudinal reinforcement, which in this case, the main bar is 16 mm, therefore your C-mean bar should be equals to 16 mm. And then you want to determine the C-mean durability. The recommended strength class is S4. Exposure class XC3, strength class S4. You know that your C-mean durability equals to 25. Now this is 16, this is 25, and you have 10 mm. You use the largest value of the 3. That gives you C-mean equals to 25, plus the deviations 10 mm. Your nominal cover, it will be 35 mm. This column is a short column. That means the MED that you use to determine the amount of reinforcement bar from the design chart, it will be on basis of the first order moment. There won't be any second order moment. Because of this, your calculations that become simpler. At least you don't need to find this MOE and you don't need to find this M2. Now if you refer to the equations for the MED, you need to find the M02 and make sure it is greater than the M-mean. M02, it will be the calculated moment, which is the summations of the moment acting onto the column plus the moment due to imperfections. The imperfection moments is calculated by having the NED, which is absolute, multiply the eccentricity EI. And this EI, it will be in the functions of the effective length. There shall be two values obtained. The greater value, it will be the M02. And that should be used as the MED to be applied in the design chart for you to find the area of reinforcement. Up to this stage, you will see the calculations, it will be similar to what we have discussed previously. This is the standard calculations. However, if you see the moments here acting onto the column, there are two moments. For the time being, we do not know which side will be more critical than the other side. Not knowing this, when calculating the first order moment, we will need to calculate for both sides, major and minor axis. Let us first look at the moment due to imperfection. We need the EI, which is given by the formulas of L0 divided by 400. The L0 is given in the questions. It seems that the effective length for the major and the minor axis differs. Why is it so? This is mainly due to the sections of the column. The different dimensions of the column will influence the moment of inertia. The moment of inertia of the column would later influence the relative stiffness and subsequently influence the effective length of the column in different axes. Substitute the L0 into the equation. L0 divided by 400 times NED, which is 147.36 kN. That gives you the EI equals to 5.7 mm. After being rounded up, the EI are the same. And then multiply NED, you get the N imperfection. This M imperfections is later to be added with the moment acting onto the column. M02 is governed by the larger value, which is 26.6 and 13.3 for the major and the minor axis respectively. The two values added up with 0.8 kN/meter. Then you get M02 equals to 27.4 and 14.1 for the major axis and the minor axis respectively. You may do the same for the smaller moment, which is acting on the lower end. The calculated value shall be the M01, as it is smaller than 27.4 and 14.1. Next, we calculate the M-mean. It is determined by the equation here, which is NED times E0. E0 is determined by the dimensions of the column divided by 30, and E0 should be at least 20 mm. These M-means are meant for the construction tolerance. Let us first deal with H divided by 30. We have major axis and the minor axis. The h shall change accordingly. For the major axis, the h it will be 300, whereas for the minor axis, the h it will be 150. 300 divided by 30, it gives you 10 mm. As for the minor axis, 150 divided by 30, it gives you 5 mm. The E-note should at least be 20. That means we should take E-notes equals to 20, since the calculated value is less than 20. Multiply E-notes with the NED, which is 147.36 kN. You will have your Eng-aim equals to 2.95. Now we're going to find the MED. For the major axis, MED is determined by M02 and M-mean, whichever is bigger. We take the bigger value. As for the minor axis, it is determined by M02 and M-mean. Again, we take the bigger value. Having the MED determined, supposingly we need to go straight to determining the MED per BH square FCK and then use the design chart. However, in this case, we have moment acting on both axes. We have calculated the moment acting on the major and the minor axis. In order to determine the amount of reinforcement bar, we cannot do the design chart separately for both axes. This might underestimate the design moment. This leads to the unit design process to generate a new MED catering for the effects of the biaxial bending before we adopt them into the design chart. In order to acquire this MED, there are two additional steps, which is unique to the biaxial bending. First, you will need to check whether can you ignore the effects of the biaxial bending. How do you know that whether you can ignore or not? We have 4 items to check. You will need to fulfill both of this plus either of this. It can be fulfilling this 3, or fulfilling this 3, or fulfilling all. If any of these 2 is not fulfilled, you will have to proceed with the biaxial bending calculations. Or if both of these are not fulfilled, then you will have to proceed with the biaxial bending calculations. This shall be used to check whether you can ignore the biaxial bending effects onto the column. In the case that biaxial bending can be ignored, then you will use the design chart to determine the amount of reinforcement bar required separately for both the major and the minor axis. The larger AS required shall be adopted. In the case that you cannot ignore the biaxial bending, you will have to enter the second steps, incorporating the effects of the other axis over the more critical side. We will check these 2 items. If the major axis is more critical, we use these equations to generate a new MED. Now, if the minor axis is more critical, then the new MED should come from the minor axis. Only then the MED shall be used in the design chart for you to acquire the AS. Having this understood, we will proceed with the design process to check for the biaxial bending. First, we need to determine whether the biaxial bending can be ignored. We need to check these 4 items. The slenderness ratios are given. This is the major axis and this is the minor axis. Take the slenderness ratio of the major axis divided by the minor axis. You get 0.54. Take the slenderness ratio from the minor axis divided by the major axis. You get 1.84. Both are less than 2.0. That means these two are fulfilled. Next, we need to check these two items. The equation here require H equivalent and the B equivalent. These are required when the column sections is not square and rectangular, which in your case now, your column is a rectangular shape. This will be the H equivalent and this will be the B equivalent. That gives you 300 and 150. Now you need to get the eccentricity in the major and the minor axis. The equations to determine the eccentricity is this. For the eccentricity in the major axis, we are talking about the MED in the minor axis divided by the azimuths. As for the eccentricity in the y-axis, we are talking about MED from the major axis divided by the azimuths. If you find these equations very hard to understand, you can imagine it in this manner. Let's say now we are dealing with the E in the major axis. The moment acting in the y-axis here, it will be the MED y. In order for you to get this eccentricity Z, you will use this divided by MED. You get eccentricity in the scale of Z. That's why you want to deal with the EZ, but you need the moment in the y-axis. Same principles goes to this EY. To get the EY, you need the moment rotating in the z-axis. Take the moments from the z-axis divided by the NED, you get EY. This explains to you why EZ you use MEDY and why EY you use MEDZ. Now you get EZ 95.7 and EY 185.9 mm. Then you substitute those values into the equations as expressed in this manner. EZ divided by the B equivalent, the whole thing divided by EY divided by H equivalent. You get 1.05. And then EY divided by H equivalent, the whole thing divided by EZ divided by B equivalent. You get 0.95. The requirements are both have to be less than 0.2, which in this case they are more than 0.2. This brings to you fulfillment of these two, but non-fulfillment of these two. That means this does not fulfill the requirements that you can ignore the biaxial bending. You have to consider the biaxial bending.